not switched on. Give me a break. It is switched. You all right? Morning, everyone. That's consistent. There was 110 of you last week, and there's 110 of you this week. Or at least roughly. So you came back. Those of you who are not here this morning, you're going to have a shop this afternoon when we do the coursework, of course. Assessed coursework will be done in the 2-hour period, finished, and we'll mark it within 3 days for you and give it back to you. So come in, come in, come in. Those of you who haven't got a handbook, anybody not got a handbook? So, you weren't here last week. So the view, right, they'll appear at that door in a minute, so I'll give them out when Tommy arrives with them, okay? If he's not already left them there, let me just check that. We evacuate the building, a little fire alarm door. So, right, to business straight away. We are 6 minutes in, so that's past my courteous time. So start at 5 past, remember? So we're going to have a little bit of lecture and then a little bit of coursework, and then maybe have a look at those tests that you did last week. Silence reigns, as always. So, did anybody do the test and then remember to bring it with them? Good, thank you. At least there's some normal human beings in here. Thank you, Phil. Thank you, Robert. See, Andrew gets to know you eventually. So, woe betide you if you cross them. And it's not just the usual cases anymore. You will be on the pass with Phil, I reassure you. You're on my list. So we're in for the coursework this afternoon. So, I'm going to break you this afternoon into groups of 8 or 7. Last year we had groups of 10. I didn't like it. You didn't like it. So we're splitting it down. So a few people will be missing. I've had apologies from at least 3 people because of circumstances beyond their control. Bereavements, illnesses, and so like, and doctor's appointments. So just come in, don't worry, we haven't started yet. So, I have a class list which I'll pass around just to sign you in again today. That's more of a relaxed class list. I also have photocopies of the groups so that you can see whose group you're in. I'll do that in about 20 minutes so you can have a little respite in the lecture, okay? Morning, young man. So, Last week we just had a quick roundup of CRE2, a little bit of catalysis, a gentle introduction. Today is a little bit more severe, but it puts you into context for what we're going to do this afternoon. So, shouldn't be too taxing. As soon as the boxes turn off, I'll give out handbooks to those that haven't got them. See, that's distracting straight away. So next time you do it, go in and find a spot on the other side, look at the back. So, timeliness, I say 5 minutes late. 5 minutes late it should be. 5 minutes, not 10 minutes late. Class disruptions, and then I'll start. Come on, you're holding up the class. Everybody look at the people entering the building because they're responsible for stopping the class. Yep, that's you in the red shoes, yep. Are we done? Right, so obviously, third years. You know, timeliness, thank you. So, introductory ideas and concepts. So we're going to talk about the catalysis. We just brought it in last week. Those of you who've got the tests, I'll give you some answers in a minute, but let's just go and start the lecture. So CRE3 moves on from CRE2. CRE2 is homogeneous. You've got your batch reactor, you've got your CSTR reactors, and you've got your recycle reactors. That's what we sort of covered, and the tests sort of brought that back to your focus. The tests are not assessed, obviously, they're just formative for you to have a play, and there are 5 tests, and if you work in a group, as you should be experienced as working in the group now, and pretty soon you'll be in your design groups, you can share the tests amongst you, and then you've got the full revision package. But I will put the tests up online for you to have a look at, and I will put the answers up online, but not immediately. The idea is you do a little bit of reading and get into the course, not I just give you the answers. So, multi-phase reactors now we're talking about. What types of catalytic reactor? Coursework this afternoon is going to introduce you to slurry reactors. It's going to introduce you to trickle bed reactors. It's going to introduce you to all sorts of things that you've never seen before without any prior knowledge. The aim of the exercise is to get you focused, to get you to realise you are engineers in your third year and final year for some of you, and you can use your noggin to work things out, even if you don't necessarily understand what the widget and the what's it is that's talked about in the paper. Okay? Quick show of hands. Who has used Web of Knowledge or Web of Science to search for academic papers? Go on, George, well done. Yes. Anybody else? George is one of our new academics, so he's joining in, and I appreciate the joining in. No? Nobody's used Web of Knowledge or Web of Science. Have we used Google to search for papers? Come on, somebody must have. Yes, okay, thank you. All right, well, Google's an imperfect way of doing it. Web of Knowledge, Web of Science is what the university pays a fortune to subscribe to a lot of journals for a lot of information. So you'll be expected in design project to go look at Web of Knowledge. So we'll have a quick look at Web of Knowledge at a break in 20 minutes, okay? If I don't, you remind me. You just say Web of Knowledge, okay? Or WOC for short. All right. So, industrial processes using catalysts. Characteristics of catalytic reactions. The 7-fold sequence of steps in a catalytic reaction, which is what we're going to do today, has formed an exam question in the past. So all this material is examinable, even if you think it's introductory. Surface volume reaction rates, interaction mass transfer surface, and effectiveness. That's basically a quick list of what we're covering today. All those are spread over the whole course. So all those concepts will come in the next 7 to 8 weeks. I'll put a note, I'll put a written document that is in effect a book chapter almost onto Blackboard to help articulate around the slides. The students in industry don't get my lectures, or they might get these voiced over slides, but they don't get my lectures, and they do about 8% better than you lot. The reason is they're only doing one course, or this year they're doing 2 courses, and you have to do the whole gambit of this. So let's have a look at what the slides say. Single phase reactor, multi-phase reactor, lots of words. Have a quick look. Single phase reactor is easy. We're only dealing with one phase in and out. If we've got a multi-phase reactor, we've got liquids, we've got gases, we've got solids. So the complexity goes up for a start off. We have problems with transport rates.
We also have problems with input rates because we're moving pneumatic conveyancing. If we're moving solids around, we've got pumping liquids, which might be viscous, non-viscous, that might come out less viscous than they went in. So you've got all sorts of problems which affect the velocity of flow through a reactor, as well as you having multi-phase means multi-flow modes. So you can, if you want to be an engineer, quantify all that with the thing in red, which is the product output is a function of the inputs, the rate equation, and the flows. So whereas before we were just dealing with rate equations in a homogeneous system, in a batch or a plug flow, now we're trying to bring up all the other items that you see there. In the notes you have, in the next page, if you just turn the booklet for me, just to remind me. Yes, you do. Okay. So in the booklet, you have a whole set of reactions that are common processes in industry. I'm not going to show you a slide of that because it won't fit. But those processes are usually taken care of with the reactor types you see there. And there's all sorts of things, but really what is the most common reactor of all, which is the most common reactor of all, you already know. Say again? Blood flow reactor. So a plug flow reactor is the most common, it's most efficient, has the highest concentrations generally, and is the one that you would go to. But unfortunately for you, not everything can be done in a plug flow reactor, so we have to then bring about liquid reactors and gas liquid reactors, and you can see them listed there. Some of you may be experiencing bubble columns now if you're using the CO2 absorber rig, so you have an idea what a bubble column might look like. They're quite fancy. We will cover some of these, but not all. But a slurry reactor, some of you are going to be reading about one of them today. Packed bed reactors, most of you are going to be reading about them today. Fluidized bed reactor and a rise-up reactor, you may indeed be reading about those today as well. Okay, that's this afternoon. So you're having a rapid learn or just a stock take of what the reactors are. So most of the reactors are plug flow. So when you get asked that question, those MSc students in the room, of which there are quite a few, when you do the online tests, which are coming up shortly, you'll know the answer to that question when it asks you. Everybody's welcome to do the online tests. Most of you decline, you don't have to, of course. But you can have a go if you like. There is negative marking, so don't just guess. And MSc students, you get 3 goes at the 5 tests, and I pick the 3 best scores overall. So you get 15 attempts, and I pick your best 3. So quite an easy set of tests, really, but it counts towards 5% of your coursework if you're an MSc student. If you're in the normal class, you don't have to do the tests, and the coursework that you're doing this afternoon, next Friday afternoon, and just after reading week, counts for 20% of your coursework. Those of you who are looking for the unit specs in the handbooks, they're in the handbooks. Read the handbooks. If you don't know what code you are, MSC's, your code begins with 6, so it's 64111. Undergraduates in the class, normally it's 30,051. Industrial students is 30,041. So it's on the front of the book, and all the unit specs are in your book. So, fluidized reactors. Now, we used to have a second-year experiment that did with fluidized bed. Do we still have the second-year experiment that does a fluidized bed? Or did they stop it when they moved us into James Chadwick? Has anybody experienced a fluidized bed reactor in second-year labs? Silence reigns, so obviously not. Okay, so what you're doing with a fluidized bed is you're using a gas or liquid to make the particles move around. That's different from a packed bed where everything's stationary. So now you're trying to agitate the bed. Why do you think you might do that, engineers? Why might you want to agitate a catalyst bed?
Surface area increases.
You said that. Where's that coming from? Yeah. You said that, sorry. Just checking where it came from. I heard the voice, but I'm looking at my man in the middle who always answers my question. Sorry, missed that one. So, say again?
Surface area increases as we fluidize it.
So the particles are now dispersed, but the surface area of the catalyst changes only because it's no longer in contact with other catalyst particles. Is that right? Okay, sort of. That means no, but nice to try. You're right, it does separate the particles. It improves something else, much more importantly. So we're heating this thing, right? So we're putting heat in from the outside generally, And we've got a packed bed, usually, which the gas is passing over or passing upwards through, whatever. And now we've decided we're going to fluidize it. It's important for you to start to think, yes?
It's increased diffusivity of the gas and the
You're really very, very technical. Remember, everything is simple. Engineers, you're blunt instruments. You're simple. Simple first, complex later. No, is the answer. Sorry. Thanks for trying.
Smaller pressure drop.
Okay, well, at least we're talking variables that make some sense. That's good. Diffusivity is too high end. You're too complicated.
Increase in transfer rate.
Yes. So you almost got it when you said you were increasing the surface area, and you almost went on to say it mixes better. You were going down that. Thanks, Tommy. So your books have arrived for those who need them. So it basically causes internal circulation in the reactor. So now we're actually stirring it around. So imagine now we're mixing in the heat. So the heat is no longer coming from the outside, it's actually being dispersed inside the bed. Also, of course, your reactants are now, as you so rightly said, have improved contact area because they're no longer stuck in clumps. So you could argue you were correct, at least in part, with increasing the surface area. So you're increasing the reaction area. So that's why that is done. Now that's a new bed, and that is one of the most significant reactors you'll ever meet in the oil and gas industry, because it is indeed a fluid catalytic cracking reactor. FCC reactor to you, which is the thing that produces the naphtha from gas oil when the crude oil is distilled. So it's the driving force behind every single person who's got a car or gets on a bus or powers something with oil. So it's the driving force behind that, and that's the most important catalytic reactor on a refinery next to a distillation column that separates it into the grades. So, bless you all around, everybody's got the sneezes. Packed bed reactor, multi-tube reactor, single tube reactor. So if we go from left to right, you're familiar with a packed bed reactor that's a small scale tube reactor. That just means it's long and thin. That means it's chunky, it's more well built, and this is just trying to do the same thing. Your blunt instruments, remember, so you're splitting that big bed into little ones, so that reaction is probably highly endothermic, so you need to get more heat in, so therefore you split it into smaller tubes, so effectively you're improving the heat transfer again. So everything's on the slides. I'll keep an eye on the clock, just in case. Is the pace okay for everybody? Are we all right? So I broke them down. I don't know if the table is in the note, to be honest. I did do it once, and then somebody corrected me and said, oh, Arthur, there's 33 reactions in the table on the next page, and you've only said 29. Oh, go cry. I can't do anything about that. It's just to give you an idea that most of the reactor types are fixed bed reactors. So most of them, 21 of the 29 that I've just quickly looked through on that page that you've got, that I don't have on the slide, with all the processes, is the majority of my buy book. So what's the percentage? Engineers, rule of thumb, remember, should have been doing this in second year, rules of thumb. Every time I go to a reaction, every time I look at a system, 21 out of 29, so let's be generous and call that 66%. So every 2 in 3 goes, you're going to get it right. But every 1 in 3, you're going to get it wrong. So it just gives you an idea when you go for your black box, what's in my reactor system, what's my black box? My black box is going to be a fixed bed reactor, unless I'm unlucky. Okay? Remember that the referendum in Scotland was lost 55 to 45, pretty much. So this is a 66 to 33. So just get the percentages in real terms and in real life, and you'll have no problem trying to do design projects. We've talked about other types and other configurations already. That was on the previous slide. But now we want to just introduce catalytic reaction engineering and another interesting point. So we've got the boundary layer. We've got gas passing over a particular solid catalyst. The slide, what's that? Turn it off. If not, George, get up, pound him to a pulp, and then we'll deal with it later. He's a big guy, you probably lose out. Don't do it. General features of catalytic reactions can increase the speed of reaction enormously. We covered this last week. Which is the scheme? Now this is a Levenspiel joke, okay? So this is how sad engineers are when they get old and grey and they write books. They think this is funny. My jokes are mildly better. Let me just. So, here is a block of platinum that's supposed to be dispersed. Is it better to have the platinum in a big lump, or is it better to have it spread over the surface? So what's the platinum? The platinum is in a solid, and it's the active component. So it's no longer this tube that everything goes through and out, magically comes all the product. Now we've got this tube with something in it that's got to convert it to the product we want. That something in it is probably, more than likely, a powder with either something on it or something built into it already. And those are called active sites, and we talked about that. So in other words, for the engineering terms that you were trying to talk about mixing and heat transfer before, it's better, of course, to have the platinum spread wide and thin. So imagine a table, look at the pieces of paper I just laid out there. If I all put them in one pile, and it's the clock, for example, that's not going to have much contact with your reactants, so it's not going to be very good. Whereas if you spread the papers all over the desk, all those are active sites, that makes a better reaction. So it's better to have a dispersed catalyst. And then, I don't know if that's written in the notes, but basically just exactly what I've just said. The extent of subdivision increases the area, obviously, and may have a profound effect on the activity and the specificity. And remember, we're going to be talking a lot about conversion, catalytic performance, and how selective a process is. And those are key words. Now, you're a particularly attentive class, which is quite nice. I quite like you already. So we should have no problem. That appeared as an exam question. Surprisingly badly done. It was only 2 marks or 3 marks. So when you see these 2 marks and 3 marks, everybody, don't just ignore them, because you get nothing if you ignore it. Whereas if you just put a sketch on it, you might just get 2 marks, and you might just help you pass the exam if you're struggling. Also, little diagrams like that are easy to get me to understand that you understand something about the course, even if you use the wrong words. Are we okay? Have we got that all written down? Are we happy? So, what does the last sentence mean? In addition, unbalanced surface forces at the catalyst-fluid interface usually play a key role. Flat table, catalytic surface. 2 pieces of paper and clock dotted around on catalytic surface are different heights, different shapes, different colours, therefore different surface forces, therefore likely to give different types of reaction or be the point of reaction. And we'll discuss that in more detail later. But if you get something simple in your mind about all the analogies that I try to give you, you'll understand the course and it will be a piece of cake.
I don't understand the last sentence.
I thought you'd say that since I tried to explain it over here. So now we have a flat surface, which to our eye appears uniform, with the exception of the 2 bits there. Okay, so that's uniform. So I'm going to say that's all the same surface forces. There's nothing on that. So every time I put a molecule in contact with that, it's going to do exactly the same thing. All right. Now I've got a real surface because I've got things on it. Now, if I look down with a microscope, I'd see that that surface was no longer flat either. But let's say I've now just made it artificially what you might see if it was a microscope. So now we've got different heights. Different colours might mean different polarity, might mean different surface charge. Hence, you've got differences. They do not react the same. Engineers, we assume that everything is the same because it fits our convenient models. And then we try to refine and refine again. But bottom line is, that is what is meant by that statement. The surfaces might look uniform to you and I, but it isn't uniform. Therefore, different things happen, and I'll give you an example in a minute, okay? So hold with me if you don't understand that. Now, you're going to design things very, very shortly with, it's Gonzalo, I think, Gonzalo Carlos Combo, followed by Colin Webb. You do not design for initial activity. So that's a curve that I might get by testing that catalyst in that bed, and it basically is a plot of the conversion of cumene, which is an aromatic compound, it doesn't really matter, conversion versus position in the fixed bed. So it goes in, it's going through the bed, and as we get the element which is being converted there, you can see we've highlighted it at that position Z, Z plus DZ. You can see that the conversion is higher than it was at the start, and it continues to get higher to the end of the bed. That is absolutely standard, that's what you'd expect. However, that's day one. You're going to design processes for day 4 years from now. Okay? And that might be the conversion by the time you get to 4 years from now. Hell of a lot different. Also, your conversion, even we can see, is about 40% of what it was at the startup. So in other words, if you put the right amount of catalyst in on day one, you're going to end up fired because you're going to be 60% short by the time you get to year 4. So you're not going to make a profit, and somebody's going to say, why the hell did you put that amount of catalyst in? You should have put 2.5 times more in. Okay, or 60%, 140% more, whatever the correct number is. Sorry, you're drawing that. I just can see that, but we're still trying to draw a lot in line. So you design for end of life, not for beginning of life. So we talked about FCC process catalysts before. We talked about a fluidized bed reactor. In a catalytic fluidized bed reactor in industry, how long do you think the catalyst lives for? So it's actual lifetime. So we put the catalyst in, it goes into this 5-meter riser cracker, and comes out the top. We've got our product and we've got our catalyst. How long is the lifetime of that catalyst? Any guesses? Think about it. Give me a number. I'll let you something useful. Where's those hands for ambles? Any answers? Come on, play the game. How long is the catalyst live for? All right then, some numbers. Is it 4 years? Is it a day? Is it a year? 6 months, thank you for playing. Oh, like pulling teeth this morning. 6 months, any advance, higher, lower? I can turn into Bruce Forsyth if you want.
10 days. Oh no, I actually have
10 days, thanks for the answer. Any more, higher, lower? 8 years. You're just being silly now.
one reaction.
Yeah. Well, it's the FCC cracking process. It does, you don't need it. It does depend on the catalyst, but it's still a very short length of time.
20 minutes.
Keep going. A minute instead. Keep going. Few seconds. Keep going. Oh, you didn't get one, all right. It lasts for between 50 to 150 milliseconds. That's his whole life. You think a butterfly doesn't live very long? His whole life. So of course you need to build a caliber powerful regenerator setup to get your catalyst back. And you go, surely not. We can't design a process in chemical engineering that the catalyst lifetime is 50 milliseconds to 150 milliseconds. Well, you have done. And it's only been working for about 70 years. So, engineering is no one fixed solution to anything. No problem. catalyst needs to be regenerated, and it is done so every 24 hours, and then recycled back in.
Sorry, just the second profile. What was the explanation for it? I mean,
That's what the catalytic activity is like at the end of the process. So why I'm saying that is not to confuse you, but it's a very important fact. And if you're having interviews and you want to know something to impress, you can say you're doing catalytic reaction engineering, you've done a bit of FCC, and they'll ask you what do you know about it, and there's something that obviously catches you by surprise. So hopefully so that's the initial activity of a catalyst. It's very, very vigorous, like me on a Monday morning. By the time I get to Monday, about 11 o'clock, I'm about that active. By Friday, I'm on the baseline. A bit like you, I guess. Oh no, you actually go the other way, don't you? You start Monday dead, and then you wake up towards the end of the week. That's right. I remember now. That's correct. Okay. So, some basic stuff. Physical absorption versus chemisorption. Okay. General features. Catalytic reaction is the interaction between the fluid phase and the surface. You got the idea. So, if we have a boundary layer, and we've got the gas flowing past here, and you're all the catalyst active sites sat on your seats, and we've got some empty seats, so those seats are not catalytic active sites, but you guys are now all the platinum sites that we saw before. Ladies, you can imagine your gold if you wish to, it's your choice, but platinum is the better catalyst. So, platinum sites, then you've got the molecule moving around, and one sensible molecule moves towards the catalytic surface across the boundary layer, and it decides it interacts with the surface. But it doesn't like what it sees, so it moves off. Then it moves back, and now it likes what it sees, so it sticks. So I'm now stuck here, and the reaction takes place, and then the products move off. The difference between that was that I stayed there a short time, and I stayed there a long time. The difference is it needs more energy to get me off from the chemical reaction than it does from just the physical absorption. You should know that, but if you want, that's a physical representation of it. It's between 8 to 24 kilojoules per mole for a physical absorption. Remember, it's a number, it's an average number, it's not absolutely 100% in stone. You might have a different number, and it might be slightly higher, slightly lower, but it's an indicative number. When you get a reaction taking place, it's generally a higher, much higher number. And we'll talk about this as we grey the boundaries between black and white during this course as we get more in detail. Next week we're going to be talking Langmuir-Hinshelwood kinetics, so we're really going to go into the mainstay of the course next week, and it'll begin to get a little bit more mystifying as you say, well hold on, that's that, and we start to make assumptions which are incorrect. We make lots of incorrect assumptions. But they just have to average out with the right answer usually, so we carry on doing it. And 2 people won the Nobel Prize for it, and I'm not to argue with them since we're still using their kinetic models today. 1934 and 1951, and even that was before I was born, for those who's asking. Right. You should know about van der Waals type interactions from Phys Chem. Yes, I know, Phys Chem's a long time ago, but some of those things you do have to remember. Strong interactions, chemical bonds. Obviously, I would hope that you would figure that a chemical bond is a lot stronger than physical interaction. So I can simply throw all those papers on the floor because it's a physical interaction. But it takes a lot more to actually break your body apart into its individual constituents. I hope you realise that. Yeah? So, chemisorption is specific, whereas physical absorption is not specific. Sounds easy, doesn't it? But when phrased in an exam question, surprisingly few people can remember that. But it's actually quite sensible. Physical absorption versus chemical interaction. It's basic Phys Chem. So, the mainstay of this course. We have arrived at the key slide. I won't bother taking names. You're either here or you're not here. So, and just take one, pass it on. Take one, pass it on. Make sure you've got one because it's got your name on it and your group number on it. I'm just going to put numbers 1 to 23 on the tables. If you need any more, I'll just have to let them go to the back. So, boundary layer is the grey carpet. We're engineers, we're passing our flow through the reactor. Unless the table's in the way, but never mind, you wouldn't design it like that, I'm sure. So now, flow's going through, we're going backwards and forwards, this is the boundary layer. So engineers, how do we reduce the boundary layer to get from here to here where I want to be, because I want to be converted into something new. I want to be the product. So I'll start at this end. How do we reduce this layer? So boundary layer, do you remember this stuff?
Could you repeat it? I was
Okay, so we've got the flow down the central reactor, which is passing past your catalysts. For the moment, we'll just assume this is the wall of the reactor, and actually it's passing over all of you. But just for the sake of this, let's make it just down here. So we've got the catalyst is there waiting for us to get to it. There's a boundary layer between me, which is the molecule that's the reactant, that wants to get to the catalyst. That boundary layer. Are you familiar with the concept? Boundary layer. Don't say no, for goodness sake. Just say maybe. Say maybe. Okay, so the boundary layer is the distance of the film thickness across that layer. Look it up. We can reduce it by increasing the flow. If we increase the flow, we shorten the distance. So the faster the flow rate, the smaller the film thickness is, generally speaking. What happens if we increase the flow through a packed bed, do you think?
just to be increased. Just to be increased.
Did you say pressure increase?
Just to be.
So you might get an increased pressure drop. So obviously there's a finite limit on how much you can increase the flow. So we're going to get across the boundary layer. So look at the diagram. The boundary layer is there. So we've got the catalyst, which is where you are all set. So across the boundary layer. That's step one. I've now got to get to the particular active site. Now it's not meant to be a heart, but I made it a heart. And there's a reason I made the active site a heart. From all of you in Asia and China direction, the sign for catalysis in Chinese, I'm allegedly told, is a marriage broker in Chinese. You can disagree with me and tell me I'm wrong later, but apparently it looks awfully similar. The symbol for marriage broker and a catalyst or catalysis is the same. So we want to get to the heart. We want to turn the product from something, the reactant from something into something. So first step, across the boundary layer. Next step, my catalytic active site is the man in yellow over there, for the sake of argument. Okay, he's got a 3 on him as well. That's quite convenient, because now I've got to get to you to do the reaction, okay? So how am I going to get there? Well, I could go up there, around there, and down there, and around, or I can fly over there, or I can walk this way. So you can see I'm having a finite time with which I have to get to my man with the number 3 on it. That finite time is diffusion. And now we diffuse through, and we arrive at the active site. Hello, my friends. So now I'm at the active site, the reaction that we want to happen takes place. You've been assuming A goes to B, and that's it. Or A plus B goes to C plus D, and that's it. But unfortunately, for A to go to B, I have to get in touch with this man, but I have to get from over there, all the way up here, to him for the reaction to take place. I then have to absorb on the side. Sorry, I'm touching you now. Big fish feel threatened. Okay, so I'm touching him, so I'm absorbing, and now I'm off desorbing, and now I'm the product, and off I go down here. And now I exit the reactor, and the class is over. No, just kidding on that last bit. Alright. Okay? So those are the steps. 1, cross the boundary layer. 2, diffusion to the site. 3, absorption on the site. 4, catalytic reaction. 5, desorption off the site. 6, diffusion back out of the particle, so I've got to get away from him and out of the reactor. And 7, I've got to get across the boundary layer so I can now exit the reactor. That's the 7 steps of catalytic reaction engineering. We're going to cover in detail this bit, because that's important to understand the mechanism of the absorption. We're going to have some basic equations that we can allow for diffusion, and we're going to play around with the boundary layer. So that's articulated hopefully in the slide. You don't need that. It's not complete. Stupid me, I left the words out. Grant Campbell's fault. Blame him. Seemed like a good idea at the time to leave a few words out in the handbook. Okay. Are we all done? Make sure you're passing those things back as well, because it's got your group names and numbers. I'll put them in the room as well, just so you know. Web of knowledge, thank you. Or Chinese cooking, if you like. Don't forget your wok. Spoke with a Liverpool accent rather than a Chinese accent. I like their wok. I said I made bad jokes, what can I do? Okay, good. Nice, easy pace. Don't worry, it gets a lot worse. Better. Mass transport and catalytic surface reaction. Okay, so we've got the bulk phase, and we're talking about getting across the gas film, which goes to the solid phase. So I'm back up at the solid phase now, at the table here. So we've got a rate of diffusion of A equals kg times the concentration in the bulk minus the concentration on the solid. The surface reaction, remember, is what the concentration is at the surface. So what you've been doing to date is you've just assumed that the concentration is the concentration in. Now you've got a shock, because now not all the concentration gets to the active site. The question to you is, do you always get 100% conversion? No. You might get damn close if it's a very fast reaction, but you should automatically assume you've not got the maximum rate before you even start. So you've got a rate equation, you've got a rate constant, you know the activation energy, you can calculate all the Arrhenius stuff and the parameters you need for the model, but you're assuming it all goes to the site, and it gets worse.
Excuse me.
Yes?
Sorry, I just had a question about this previous slide. The one with 7 steps.
Yes?
Yeah, the one before that.
Uh-huh.
Why does the reaction start as the... Well, why doesn't the reaction start after the first step? When it first touches the catalyst?
Oh.
Shouldn't it all be the same?
So then we have the concept of the active site, which you may have missed, and others may have missed as well. So it's a good question. So we're assuming that the only reactive site in our catalyst is my man in yellow, number 3 on it. Okay? Because why is a good question. We can go why until we get to the end of it. Because active sites are either what we make them to be, or the material itself is sufficiently amenable to the catalytic reaction. An active site is not just a catalyst, which is a powder. So that surface you're leaning on is not doing the reaction now, is it? It's not burning a hole in your arm. Your arm's not disappearing because it's reacting. It's not an active site. It's just an absorption surface, typically absorption surface. Catalysts require active sites to do their job. Why do they lower the activation energy of a reaction to make the thing go faster?
Now, why don't we have the homogeneous catalyst all the way that the whole thing is the active site?
That's a very good question and quite advanced. So can we hold the thought? Yeah? Because we'll find out there are lots of different kinds of catalysts, which are eggshell, egg yolk, homogeneous, and that will mean something in a little while. Unfortunately, I forgot to bring a marker pen again that works on this damn board, and still no marker pens. It's a very good question. Do not think you don't understand. You do understand, but for the sake of this example, we're only interested in the catalytic site, which is there. Okay? And for the sake of argument, we can't manufacture something like that, but for this demonstration, that's correct. Thank you. So, mass transport across the bulk to the surface reaction. We've got the two equations and we make them equal to one another because we assume it's an equilibrium process. So we're going in, we're going back, we're going in, we're going back. So we're doing it all the time over all the catalysts. So you've now got a very nice reaction which is balanced, which means you can rejig the equation as you see there. Nothing particularly exciting about the algebra. But the equation reduces to the concentration. The rate is equivalent to or equals the two constants, which are additive, times the concentration in the bulk. 1 over, of course, those constants. That's a nice, simple reworking, which you can do yourselves, just to make it prove to yourselves it's okay. Has everybody got whose group they're in for the coursework this afternoon? Where did it stop? You haven't at the back either, okay? Just so you can keep it with you and be comfortable in the knowledge. Did you not get them either? You don't got these groups. There you go, take one, pass it on. I photocopied 160, so it's not possible to get rid of them because there's only 110 of you. Rightio. Where's your next lecture? In Reynolds or is it Simon Building? You should say that. I'll show you about web of knowledge next time. We've got 1 minute to tend to, but you've got to get down to Simon Engineering, have you? Bloody hell. Okay. We'll stop there then. Because you haven't got time otherwise. Come on, you've got to go to Simon Engineering, you're not moving. Where they all wait because there's can add